Welcome to Circuit Secrets. This video is the first in my course on basic electronics. In this video I will cover electricity. In basic electronics, the first thing to learn about is electricity. Electricity makes all electronics operate, and electricity in some cases can and will destroy electronics. Warning! Not only can electricity destroy components, but it can cause serious bodily injury and even death. Electricity presents an electrocution hazard and can cause severe burns and fires. This video is intended to help the viewer understand electricity, but is not intended to serve as electric safety instruction. Electricity is used every day all around us. It powers our lights, our air conditioners, cars, smartphones, and more. Its uses seem to be limited only by our imaginations. So what is electricity? In electronics, the term electricity is the flow of electrons through, or more precisely, upon the surface of a conductor. A conductor is a material that electricity can easily pass through. The typical conductor is copper wire. The flow of electrons creates what is called electric current. Electrons are negatively charged particles, and their flow or electric current can be used to perform work. You can think of electrons as tiny balls that move along the path of the circuit, through the conductors. Many metals are conductors. Some conductors are better than others. A metal like copper is pretty good at conducting electrons. Some materials and alloys, like nichrome, will convert electricity to heat and do not work well for transporting electricity. Copper wire will also heat up if too much electricity is passed through it, and this heating can be reduced by increasing the diameter of the wire. We measure how effectively a material or component can pass electrons as the value's resistance or conductance. The more resistance or higher the impedance a material has, the more it restricts or resists the flow of electrons. Resistance is the opposite of conductance, which is the ability of a material to carry a charge. With a wire, the resistance increases the smaller the wire is. Resistance wastes electric current and converts the wasted energy to heat. This heating is useful for building things like electric heaters. If you have ever examined a wire used for transporting electricity, you will have noticed it is coated in a plastic, rubber, paint, or in the case of an antique, cloth. This coating is an insulator. An insulator is a material that will not conduct electricity. Insulators are important to keep the electrons traveling through the paths we want and not taking shortcuts. When electricity takes a shortcut, preventing a circuit from operating as intended, we call that a short or a short circuit. There are three states of electricity that you can expect to encounter: direct current, alternating current, and static electricity. Direct current electricity occurs when electrons flow from a high concentration of electrons to a lower concentration of electrons in one direction only. The difference in charge from positive to negative is referred to as electrical potential. DC electricity can be imagined as balls rolling downhill from a high place or high potential to a lower place or low potential. The electrons always seek an equilibrium of charge the same way water seeks its own level. Batteries hold a static charge and use this charge to produce direct current. When they run down, there is no longer a difference in charge or potential from one terminal to the other. Alternating current, or AC electricity, can be thought of as electricity that changes polarity at a given frequency. Alternating current behaves differently at different frequencies and produces many different effects in electronic circuits. A sound signal is alternating current. A radio signal is alternating current, and the power distribution systems that provide electricity to businesses and residences use alternating current. Static electricity is a stationary charge until it meets a difference in potential, at which point the charge starts flowing from high potential to low potential as direct current. Lightning is a form of static electricity. Static electricity can be very destructive to certain electronic components if it possesses enough potential. This is why there are electrostatic-proof containers for sensitive parts and anti-static wrist straps to discharge an electronics technician before handling such parts. Now that I've covered some of the simplified basics of electricity, I will introduce you to the deeper physics behind electricity. All materials, liquids, solids, gases, contain two particles of electric charge with two polarities. I've already touched on electrons, which are negatively charged or have a negative polarity. The other particle is the proton, which has a positive charge or positive polarity. The smallest negative charge possible is a single electron. A proton holds a very small positive charge. A charge always has a polarity, either positive or negative. Polarity can be thought of as the two natural states of many systems in physics. The poles of the Earth or the poles of a magnet are examples of opposing polarity. The poles of the Earth and magnets have a magnetic polarity. One pole of a magnet is thought of as north and the other as south. The north pole of a magnet is drawn to the south pole of another magnet, but like poles repel. It is the same effect with the polarity of electrical charges. Negative charges are drawn to positive charges, but like charges repel. Polarity is also used to explain other more complicated effects. If you have a wire that is not connected to anything, there is no evidence of electricity. If it is connected to a voltmeter, which is a device designed to measure electricity, there will be no indication of any charge. This is because the protons and electrons in the wire cancel each other out. It can be said that electrons and protons have equal and opposite charges. Work has to be done to push electrons in order to produce usable electricity. This work can include rubbing balloons on your hair or a sweater to produce a charge, passing magnets over wires as is done in a generator, using chemical energy to separate charged particles in a battery, or any other number of methods. The terminals of a battery are marked positive and negative to indicate the polarity of the charges and the output of the battery. In an atom, the protons are found in the nucleus and the electrons are found orbiting the nucleus. The proton is larger and more stable than the electrons in an atom. There is also the neutron in the nucleus of the atom, but it holds no charge, is considered neutral, and has little to no effect on electricity. An atom naturally tends to have a balanced charge, as the electrons and protons are drawn to each other and tend to cancel the opposing charges out. This is the structure of the simplest atom, the hydrogen atom. The hydrogen atom contains one proton in the nucleus and one electron in orbit of the nucleus. The electron in a hydrogen atom is considered to be orbiting the nucleus of the atom, forming an electron shell or electron energy level of the atom. The charges of the proton and the electron cancel each other out, making the hydrogen atom neutral and in a state of electrical balance. With other larger and more complicated atoms, the electrons arrange themselves at different positions in different shells or energy levels of the atom. These energy levels or shells have different radiuses, just like the orbits of the different planets that circle the sun. All of the protons in an atom are found in the nucleus. The total number of electrons in shells or energy levels of an atom must equal the number of protons in the nucleus of an atom for the atom to have a neutral charge. The number of electrons in different shells around the nucleus determines the element's electrical properties. The energy levels or shells of the atom can be numbered starting at 1 next to the nucleus with an absolute maximum of 7 if using their principal quantum number, or K through Q using alphabetical notation. The most important electron ring when it comes to electrical properties is the one furthest from the nucleus, the outer shell or the highest energy level of the atom. According to Bohr's model of an atom, the formula for electron arrangements of the atom follows the rule 2n squared. The first orbit or shell can contain a maximum of 2 electrons. The second orbit or shell of the atom can hold a maximum of 8 electrons. The electrons in the outermost shell or orbit of an atom are called valence electrons. The valence of an atom must contain 8 electrons for the atom to be considered electrically stable, unless the atom has only one energy level or shell, in which case the outer shell of electrons can contain a maximum of 2 electrons for it to be considered stable. The outer shell numbering 8 electrons for electrical stability is called the octet rule. The value of the valence is based on the number of electrons in the topmost energy level or shell of the atom. Carbon is said to have a valence of 4 or -4 depending on how you look at it. There are 4 electrons, which is 4 shy of the 8 required for a complete valence. Most shells or energy levels of the atom are divided into subshells, but this distinction is not really important when it comes to the study of electricity. If we examine the valence electrons of a copper atom and compare them with the valence electrons of a carbon atom, we find that carbon is more stable than copper. This is because carbon has 4 valence electrons and copper only has 1. When copper atoms are packed together tightly to form a wire, the atoms have a tendency to share the valence electrons as they break free and pass between atoms. These mobile electrons are called free electrons. Free electrons are what gives copper the ability to easily conduct electricity. These free electrons pass from atom to atom in random patterns, and so a wire has no natural polarity or overall charge. However, if a voltage potential is applied to the wire, and the wire sees a potential of charge from one end to the other, all of the randomly moving free electrons will travel in one direction and produce a current. This potential charge looks like 2 charge states to the wire, with high potential on one end and low potential on the other end. Carbon can pass electrons, but its higher stability causes it to resist the flow of electrons. This is why carbon is commonly used for the manufacture of a component called a resistor, while copper is used as a conductor in the form of wires or traces on circuit boards. A resistor is a component that has a defined resistance to the flow of electricity. Atoms can have 3 basic electrical properties. The material can be a conductor, a semiconductor, or an insulator. A conductor is usually a metal such as copper with a lot of free electrons. A semiconductor can conduct electrons but causes some resistance such as carbon, which we examined earlier, or silicon, which is used to produce transistors and microchips. Semiconductors have 4 valence electrons, halfway to the stable 8-electron configuration. An insulator is an element that is electrically stable, which prevents electrons from moving freely from its upper shell or orbit. An insulator is also a dielectric, meaning it can hold or store an electric charge, like the static electricity example I mentioned earlier. A group of atoms is called a molecule. Different elements can be combined into compounds to form molecules that have different electrical properties than the elements alone. This is because of the way the electrons can share the orbit of multiple atoms, which changes the electrical stability of the molecule. The atomic number of elements is used to determine the structure of the atom. The element hydrogen, for example, has an atomic weight of 1, which means it has 1 proton, which must be balanced by 1 electron. Because the hydrogen atom only has 1 shell or energy level with only 1 electron, and an atom with 1 shell is considered stable if it has 2 electrons, hydrogen is considered unstable. This is why hydrogen can react so easily to combust in the presence of oxygen. Oxygen has 6 valence electrons, which means it is slightly unstable. The instability of both hydrogen and oxygen causes them to easily and violently combine if exposed to very little energy, such as a spark. Oxygen and copper can easily combine as well, but this reaction is not normally as violent as hydrogen and oxygen. Copper and oxygen produces copper oxides, which are dark-colored and electrically stable, meaning they are poor conductors. Sometimes electronics fail because of oxidized wires and connections. The oxidation of conductors and connections is called corrosion. Now that I've covered how and why electricity works, I will now examine the measurement units related to electricity. The study of electricity began with the study of lightning, and as such the first measurements I will teach you are related to electrostatics, or the study of static electricity. Stationary charges are contained in dielectric materials. Sometimes these charges have an abundance of protons and a shortage of electrons, and sometimes they have an abundance of electrons with a shortage of protons. If you rub a plastic pen on a piece of paper, the 2 materials will become attracted to each other because one has an abundance of electrons and the other has an abundance of protons. Batteries contain static electricity. A charged capacitor contains static electricity. The measure for a charge is the coulomb. 1 coulomb is equal to 6.25 times 10 to the 18th power electrons or protons stored in a dielectric. If you do not already understand the scientific notation of values and/or want me to make a video about it, let me know in the comments below. If you are enjoying this video, please don't forget to like and subscribe. In formulas, the coulomb takes on the symbol C, and Q is used to indicate the quantity of an electric charge. So an example would be Q equals 1C. The polarity of the charge is indicated by a plus or minus sign. So if there is an abundance of protons, the charge is written as plus Q, while an abundance of electrons is written as minus Q. The charge of a single electron is indicated as negative Q equals 0.16 times 10 to the negative 18th power C. Since an electric charge attracts or repels other electric charges the same way magnetic poles attract or repel other magnetic poles, it is common to visualize lines of force associated with electric charge in a similar way to the way we visualize magnetic lines of force. This is the way to visualize electrical charge lines of force because a charge will exert equal force in all directions. The next measurement is voltage. Voltage is a measurement of the potential between 2 points with different charges. An example of the 2 points one may measure is the poles of a battery. One pole of a battery is said to be positive, and one pole is said to be negative. The measurement of voltage indicates the difference in potential between the 2 poles. It is important to understand this measurement is not absolute, but a relative measurement. In other words, the overall charge of the battery may be the same as the charge of the table, but it is sitting on. But the battery still contains a potential and difference in charge between the poles of the battery, not between the battery and the table. Think of it this way. The battery may have the same total number of electrons and protons with or without a charge. But when the battery contains a charge, those electrons are separated in such a way that the poles have a potential between them. The definition of 1 volt is the potential when 1 joule of energy moves 6.25 times 10 to the 18th power electrons, or 1 coulomb of electricity. 1 joule of energy is 0.7376 foot-pounds of motive force. This formula can be shortened to V equals 1J divided by 1C. Another variation of the formula is V equals W divided by Q, or voltage equals work divided by the quantity of the charge. The next measurement is current. Current, put simply, is the flow of electrons through a conductor. But it goes much deeper than that. A current occurs when the potential between 2 charges causes a third charge to move. The first 2 charges can be the potential on the terminals of a battery, and the third charge is the free electrons in the conductor. As electrons enter the conductor on one end, they push the free electrons in the conductor away from themselves. The relative positive charge on the other end of the conductor, at the other terminal of the battery, draws the free electrons to it. It is a different electron that exits the conductor than the electron that entered the conductor on the other end. However, since all electrons are the same and can be considered fungible or indistinguishable one from the other, it makes no difference to the elements and charges which electron entered and which electron exited the conductor. When current is moving through a conductor, it produces a magnetic force. This magnetic force is always at a right angle to the current. This is called the right-hand rule. Although electron movement is how we typically imagine current flowing, sometimes protons can flow and move to provide currents. However, this usually occurs in a gas or a liquid. The measurement of current is called amperage, the ampere, or simply the amp. 1 amp of current is equal to 1 coulomb passing through a conductor per second. So you can see now amperage is a measurement of a charge moving over time, while voltage is the potential difference in charge. Charge is the static state of potential, such as electrons in a dielectric, and current is the movement of that charge over time. The formula for amperage is I equals Q divided by T. Intensity equals quantity divided by time, or 1 amp equals 1 C divided by 1 second. The next measurement is resistance. We have already talked about the basics of resistance and how it is in opposition to the flow of electrons or current and how it burns off energy as heat. The measurement of resistance or impedance is the ohm. 1 ohm is defined as the amount of resistance needed to develop 0.24 calorie of heat when 1 ampere of current flows through it for 1 second. We use the letter R for resistance, and the symbol for the ohm is the Greek symbol omega. There is also the value of conductance, which is simply the reciprocal of resistance. The symbol for conductance is G. The formulas for resistance and conductance are R equals 1 divided by G, or G equals 1 divided by R. Now that you're familiar with some basic measurements, attributes, and the behavior of electricity, the next step is to learn how these features can be applied to actual circuits. In this section, I will show you some of the basics of schematics. You will learn a few schematic symbols and the basic structure of a circuit. The first schematic symbol to learn is the symbol for a power source or a battery. The symbol for a battery looks like the physical structure of a traditional battery. A traditional battery has metal plates and dielectrics separated by an insulator. This assembly is drawn like this. A resistor, which we have already learned is commonly made from carbon, has a symbol that looks like a zigzag. A resistor has no polarity and behaves the same way either way it is connected in a circuit, just like a conductor. Lines indicate conductors and circles indicate connection points. This drawing shows a basic circuit. The resistor symbol in a drawing can mean a resistor, or it can be a placeholder for a more complicated circuit and simply indicate the impedance of the circuit. A circuit's resistance is used to calculate many features of the circuit. In this circuit diagram, the circuit is closed, meaning there is a complete connection from the positive terminal of the battery through the circuit and into the negative terminal of the battery. When a circuit is completed or closed, it will pass current for as long as the power source can maintain a charged potential. This diagram is an open circuit. The path is not complete for the electrons to leave one terminal of the battery and return to the other terminal. This means the circuit will not pass current. This is another way to draw a power source connection for a circuit. The plus indicates a positive source, and this symbol indicates a ground connection. With this arrangement, it is assumed the ground has a common connection with the negative connection of the power source. It is possible to measure the voltage of a circuit without changing the circuit. The voltage potential is simply measured across the positive and negative sides of the circuit. To measure amperage, the current through the circuit must be measured. This means one end of the circuit must be disconnected from the power source, and the measuring device must be connected in line with the circuit. This is the difference between a parallel and series circuit. To measure voltage, the measurement device is connected in parallel to the circuit. To measure the current, the measuring device is connected in series with the circuit. Remember this, current cannot exist without voltage, but voltage can exist without current. Any circuit is a load on a voltage source. Sometimes a circuit will draw too much current for the source to keep up. When this happens, damage can occur to the power source, and a power source like a battery can overheat. Conventional current is considered to flow in the opposite direction of electron flow. So electrons flowing from negative to positive generates a conventional current flow from positive to negative. This is the symbol for an alternating current source in a schematic. Resistance and conductance affect alternating current exactly the same way as they affect direct current. Now that I have covered some of the measurements of electricity, I will show you some basic test equipment and how to take some measurements of circuits and electricity. The most important piece of equipment for working on electronics is the multimeter, or the modern variation, the digital multimeter. A multimeter has multiple modes, and depending on the price and quality of the meter, it can measure any number of properties of electricity, electronic components, and electronic circuits. The most basic multimeter can measure voltage in DC and AC in a few scales or using different multipliers, and resistance using a few scales or multipliers. A fair quality multimeter for electronics work will at minimum also have the capability to measure current. To measure voltage with a digital multimeter as shown, you must first select the correct mode of the meter. Some meters have an auto-ranging feature, and other meters must have the range manually set with a switch. If the range is set too low, say to a 10-volt scale, and the meter is connected to 200 volts, the meter will most likely be damaged. If, however, the meter is set to a scale of 200 volts and a measurement is made on a 9-volt source, the meter will not be damaged, but the accuracy may be impacted, and there's a chance the meter will not measure the voltage correctly. This is particularly a factor on older meters. This is the way a connection is made to measure voltage with a multimeter. The positive terminal of the meter is to be connected to the positive side of the power source. The negative terminal of the meter is to be connected to the negative side of the power source. Traditionally, the red lead on the meter is positive and the black lead is negative. If the meter is connected backwards, the meter, especially old meters, could be damaged. The meter is connected in parallel to the circuit and the reading is made. When measuring current, the meter must be placed in series with the circuit. This is the way a multimeter is connected to measure current. The positive terminal is towards the positive source, and the negative is towards the negative source. When measuring current with a multimeter, set the meter to amperage or amps before connecting the circuit. It is best to have a meter that can withstand the maximum current of the power source if you connect it to measure current. Power sources have a value in amps that they provide. This value should be printed clearly on a surface that a technician can easily read. For example, a power supply that plugs into the wall may provide 100 milliamps or above 2 amps. This value and the output voltage as well as the input voltage should all be marked on the power supply. A typical multimeter may have a maximum current rating of 500 milliamps, or maybe 5 amps, or any value. A meter with a higher rating will not harm the circuit, but if the meter has a lower rating than the circuit's power consumption, the meter could be damaged if connected. Finally, there is the measurement of resistance. This measurement requires the circuit to be disconnected from power. It is best to measure individual resistors with a multimeter in the resistance or ohm setting and with the component disconnected from the circuit to prevent false or inaccurate readings. If you attempt to measure the resistance of a circuit with power passing through it, the meter may be damaged. If you found this video helpful, please like and subscribe and turn on notifications to be updated when I upload more videos. Thanks for watching.